All right, honors chemistry people, we are going to start quantum mechanics today. So you should have your book open to chapter 5, and we're going to expand our definition of the atomic model right now. So when we left off before we did nuclear, our atomic model was the Rutherford model, where we have the nucleus in the middle of the atom. And within that nucleus, we have the protons and the neutrons. And then we have the electrons kind of buzzing around. Now, if you've paid attention in your previous science classes, you will know that the nuclear model of the atom is not 100% accurate. And we still have a couple iterations of the atom model to go through. This is going to bring us to what we currently have of the model. There is a model in between that's called the Bohr model, and we'll talk about the Bohr model more when we do energy, because the Bohr model is really important when we do energy. But we're going to talk about the quantum mechanical model of the atom for the next couple of days. And this is our current model. Now, once again, we've had this model of quantum mechanics for about 100 years now, give or take 80 to 100 years. And we're fairly confident that this is the model. But once again, most of the people that came up with models previously that have since been discarded were pretty confident that their model was correct. So the truth be told, we're not sure that this is indeed the model, and we're trying to figure out a lot more about the model of the atomic theory with the Hadron Collider in CERN, Switzerland. It's giving us some answers and making some things kind of have to change. So let's start with the first question here. What is the theory of the structure of the atom from Rutherford's gold foil experiment? We already talked about that a little bit. It is the nuclear model. Is that what we believe today? Kind of not. We still believe we have a nucleus in the center of the atom, and we still believe that the nucleus contains protons and neutrons, but we now know that we have a whole bunch more subatomic particles like neutrinos and quarks and bosons and Higgs particles and all kinds of things like that. That is beyond the scope of this class. So the nuclear model for Rutherford is a simple version of what we really think is happening. But once again, we're still trying to figure out what's really happening. So let's talk about some of the quantum mechanic guys. Now, you'll notice that most of these guys are German. Quantum mechanics came out of the chemistry/physics study in Germany and Austria. So the first guy we're going to talk about today is Werner Heisenberg. Werner was part of the Nazi regime. He actually worked under Hitler for a while. So Heisenberg, brilliant scientist, worked for the wrong team, but brilliant. So Heisenberg pointed out that in order to find the exact position of an electron, we had to be able to look at it. And to be able to look at it means that we have to have an object that we can see with our eyes. And the only way that we actually look at things with our eyes is we actually have photons of light coming off of the objects into our eyes, and then our eyes transmit those photons into neural signals that our brain transmits into images that we see. Now, remember, electrons are incredibly, incredibly small. Photons aren't much smaller than electrons, okay? So in order to see, we have to have something hit by a photon, and that photon has to go into our eye to be able to be translated into a neural image. So think about this. When a normal big object that we can see, like this water cup that I have, is big enough for photons to hit and our eyes to see, this is so massive compared to photons that when photons hit it, it really doesn't matter. But because electrons are so small, when a photon hits it, it is going to be a collision of something that is almost the same energy. And right now we're not sure, but we have massed photons. We have some experiments say they have mass and some experiments say they don't have mass. So think about this. If you're driving down a highway and you are hit by a car that is the same speed and the same mass as your car that you're driving, is it going to change the direction that your car is driving? You bet it is. It's going to change it dramatically. So let's think about this. A collision between a photon and an electron results in a large change of energy for that electron. So if we can see an electron with some sort of radiant energy, we would not know its velocity because we have just hit it with a photon and changed its velocity. And we have also changed its direction that it was normally traveling in as well. Thus, we could know the position at that instant, but we would not know the speed, and we would not know the direction that it's traveling in. So another analogy here is, imagine I filled up a room and I blacked out the room, so it was pitch black, and I filled up the room with a couple helium balloons, but it wasn't totally full, just a few helium balloons. And I asked you to go in that room and find where those helium balloons are. Now, if I asked you to find a helium balloon in a totally dark room where you could not see anything, the only way that you could find that helium balloon is to walk around and touch it. And we all know what would happen to that helium balloon if you touched it. It would no longer be in the location that you originally found it in. And it would no longer be traveling in the velocity that it normally was traveling in. So we might know its location at that split second, but we're not going to know it for very long, and we aren't going to know the velocity. So we cannot know the location and the velocity of an electron at any given time because of that collision with the photon. Okay? So, on the other hand, if we can measure the velocity of the electron, the position changes. Now, I want you to remember that the electrons travel almost at the speed of light within those elements, within those atoms. So the velocity is so quick that if we do know the velocity, that position is going to change so quickly that we're going to lose that electron again. Okay? So Heisenberg stated that there was always some uncertainty about the position and the momentum of an electron. This is known as Heisenberg's uncertainty principle. So the uncertainty principle basically means I cannot know both the position and the velocity or momentum of an electron at the same time. I can know one or the other, but not both. Okay? All right. Next guy. So scientists now, we're trying to figure out where these electrons are actually located, but scientists now, with Heisenberg's uncertainty principle, now found themselves unable to describe the exact structure of the atom. Because if I don't know where those electrons are or the velocity, like what's the structure? So Heisenberg stated that the exact motion of an electron is unknown. Okay? Notice that Heisenberg treated an electron as a particle. He treated it as a thing. What if it were treated as a wave? It looks like I've got a typo here. What if it were treated as a wave? So, Schrödinger treated the electron like a wave and developed a mathematical equation to describe the wave-like behavior that Schrödinger was able to observe. With this equation, Schrödinger was able to find an area of high probability where the electron could be found. Now notice we are not talking about exact location. We are talking about a highly probable location. Okay, so probability starts getting into this. The electron moves around the nucleus, passing through points of very high probability more often than through other points. So we can map out these areas of high probability. The electron's traveling at high speed, almost the speed of light. If the electron were visible to the eye, it would appear to look like a cloud. Okay, think about what a fan looks like when it's going really fast. You can't see the individual slats on a fan when it's going, or blades on a fan. It looks like a blur. So the electron's going to look like a blur as well. It's going to look like a cloud. Thus, the orbital of an electron is often referred to as an electron cloud. So we have currently an electron cloud model. Erwin Schrödinger's equation has helped us divide a set of quantum numbers to describe the position of the orbiting nucleus. So I want to go back up to this really big blank spot right here. We have 4 quantum numbers that we use to describe the position. And I want, if you've ever sent a letter, snail mail, I know a lot of people don't use snail mail anymore, but this is my analogy. It's very much like an address. We have 4 quantum numbers. So we have an N number, we have an L number, and that L is kind of a cursive L. We have an M number, and sometimes it's called an M sub L number. Or actually, let me think about this. Some people call it an L sub M number. Okay, and then we have an S number. And then some people call it an L sub S number. Okay, so I want you to think of the N number as, we're going to pretend like this letter is going somewhere within the United States. So this is the state that that letter or that envelope is going to. L is going to be the city or the town where that is going to. And L sub M, or the M, is going to be the street. Okay. Or I could also say the actual house. We could even get it down to the actual house. And then the S is going to be the person. The person that letter goes to. It's going to be the individual person. So sorry, that's my dog. She's going crazy. So in this analogy, this is going to be our energy level. Okay. This is going to be our type of orbital. This is going to be the actual orbital. And this is going to be the spin of the electron. Okay? There are mathematical rules that these go by. So I'm going to go over some of these mathematical rules. I'm going to do some examples, and hopefully we can get through these really quick. Okay, so here we go. Quantum mechanics. In order to locate an electron in an atom, there are 4 quantum numbers, and I already went over them. There are N, there's L, there's M, and there's S. Okay? It's kind of like an address for an electron. Okay? It gives us an idea of where that electron is. For each quantum number, there is a physical representation and mathematical values that a particular number can have. Okay? So let's take the biggest and we're going to go down to the smallest. So we're going to start with n. Okay? The n quantum number. This is called the principal quantum number. Okay? I want you to think of an n quantum number as the energy level. So it is the energy level that an electron has. Okay? Now, mathematically, n is always an integer. It's greater than or equal to 1. So if it's an integer greater than or equal to 1, we can have 1, 2, 3, 4, 5, and so on. Okay? So if the electron here is in the first energy level, if it's in the first energy level, that means n is going to be 1. Okay? If the electron's in the fourth energy level, that n number will be 4. Okay, so it's just energy levels. Now I want you to get out your periodic table and I'm going to show you how this matches up with your periodic table. So I'm going to grab our periodic table really quick. Now remember when I told you that the periodic table is divided into periods and the periods are the rows? Those periods are the quantum numbers, or the n quantum numbers. These are energy levels. So if we look at this periodic table, over here to the left, we have our energy levels, okay? Those energy levels are the n numbers. So if I look at this, here's n equals 1 is going to be this row right here. So it consists of just 2 elements. N equals 2. It's going to be this row right here. So I consist of 8 elements. N equals 3 is this whole row, another 8 elements. N equals 4 is this whole row. Okay, I should put the arrows all the way. N equals 5, and so on. N equals 6, and n equals 7. Okay, so if we look at this, our n quantum number is just what row does that electron come from? That's all it is. What row does that electron come from? It is the energy level. Okay, so let's look at our next number. Now, this is kind of a bad representation. It's L. We're going to use a quantum, or not a quantum, we're going to use a cursive L. I need to find a better font. So the L quantum number is the sublevel that electron is in. It basically tells us the type of orbital that the electron is in. Okay? We have 4 main types of orbitals. We have s orbitals, p orbitals, d orbitals, and f. Okay? So let's look at the mathematical relationship here. L is also an integer. So it has values that range from 0 to n minus 1. So for example, if n is 1, n minus 1 is 0. So if n is 1, L can only be 0. If n is 2, let's see, I will have 0 and n minus 1, so 2 minus 1 is 1. So I will have L values of 0 and positive 1. If n equals 3, I will have L values of 0, 1, and 2. So if I have n equals 4, I will have L values of 0, 1, 2, and 3. Okay, so here we go. The first 4 values of L have special names that we are going to learn. So when L equals 0, I have an s orbital that I'm talking about. If L equals 1, I have a p orbital that I'm talking about. If L equals 2, I have a d orbital that I'm talking about. And if L equals 3, I have an f orbital. Okay? So it basically tells me the shape or the type of an orbital. For an example, an s sublevel, an s orbital is a sphere. It's the simplest shape that an electron can make in terms of its wave function. A p sublevel has a kind of like a figure 8 shape, or like an hourglass, or even like a dumbbell shape. And D sublevels have kind of a clover leaf shape, 4 out of the 5. The 5th one has kind of a barbell shape with a donut around it. Let's do some looking at the graphics here. So notice this is my s orbital right here. My 1s orbital is smaller than my 2s. So if I go to my second, this is my first energy level. Is it not letting me draw? This is my first energy level, 1s. And this 2s right here would be my second energy level with the s orbital. Okay, notice every time we put another energy level on it, that orbital is going to get a little bit bigger. Now my p orbitals, like I said, have kind of an hourglass or a figure 8 shape. We have 3 p orbitals. We have one along the x-axis, one along the y-axis right here, and one along the z-axis. Now in math, you're used to doing things on the Cartesian grid, which is just 2-dimensional, x and y. Our life is not 2-dimensional, it's 3-dimensional. So I need you to start thinking in 3 dimensionals. We're going to start thinking in x, y, and z. So 3 dimensionals. Okay? Let's look at the d orbitals. Okay? D orbitals, I said, were kind of like a clover leaf. We have dxy, which is within the xy plane, but in between the axes. We have dxz that's on the xz plane, but in between the axes. We have dyz that is on the yz plane, but in between the axes. And we have dx squared minus y squared, which is within the xy plane, but right on the axes. And then we have our dz squared, which is our oddly shaped one with the hourglass with the donut in the middle along the z-axis, okay? Now, f orbitals are even more involved. They kind of look like, if you've ever played jacks before, they look like a jacks. So they have like 8 lobes sticking out of them. They're really amazing. They have some really cool geometries. So back again, these L levels tell us whether we have what kind of an orbital we have. So if L is equal to 0, we have an s orbital that's a sphere shape. If L is equal to 1, we have a p orbital, kind of like an hourglass or a figure 8 shape. If L is equal to 2, we have a d orbital that's kind of like a 4-leaf clover shape. And if L is equal to 3, we have an f orbital that's kind of like a jack's shape. It's got all kinds of spikes on it. So those are our first 2 main quantum numbers, okay? Now, our m quantum number, sometimes this is called m sub L. Okay, is this not going to let me write? want to draw. So if I have an M sub L, why isn't this letting me write? This is getting really frustrating. It represents the actual orbital that the electron is in, okay? M sub L. Some to L sub M. I've seen it both ways. M sub L is probably the more common way. Okay, it tells us the actual orbital it is in. It represents the actual orientation in space. So for example, on the P or the D orbitals, is it this one, or is it this one, or this one, or this one, or this one? It tells us which one of those orbitals it actually is in, okay? That's what the M sub L number gives us. It tells us the actual orbital that the electron is in, okay? Oh my. Oh, my computer is having a really hard time right now keeping up with what's going on. Okay, so let's get back here. So the M sub L number, this number represents the orbital that it's in. It essentially represents the orientation, whether it's the XY, whether it's the one along the Z-axis or whatever, which orientation that orbital is in. Mathematically, M can have values that range from negative L to positive L. So for example, if N is 3, L can have values of 0, 1, and 2. Let's pick 2. So if I am 2, that means I am in a d orbital, correct? So that means I can have orientations from -2 all the way up to +2. So my M sub L numbers, or my M numbers, can be -2, -1, 0, +1, and 2. That means I'm going to have 1, 2, 3, 4, 5 orientations. Let's look at our d orbitals. How many orbitals do we have in our d orbitals? We have 1, 2, 3, 4, 5. We will have 5 orientations when we have d orbitals. Okay? So, for example, let's do a p orbital. So we'll do the same example. If I have n equals 3 and L equals 0, 1, or 2, let's choose 1, okay, which is a p orbital, right? So that means my M sub L, or my M numbers, can equal negative L, which is -1, 0, all the way up to +1, which is going to be 1. This gives me 3 orientations. So I can have things oriented 3 different ways. Let's look at a p orbital really quick. So if I look at my p orbitals, lo and behold, I have 1, 2, 3 orientations that I can have. I can have on the x-axis, on the y-axis, or the z-axis. Okay? So it just tells us what orientation and which orbital that electron is in. These orientations represented by the M, or the M sub L quantum number, can range from -L to +L. So first, what are the numerical values for a p sublevel? So a p sublevel of L is 1, right? Our L number is going to be 1. So that means that M can have values of -1, 0, and +1. Okay, and we already did a D sublevel right up here already. Okay, we call these M or M sub L values. Each orbital can hold 2 electrons and only 2 electrons. Okay, I shouldn't say only 2. An electron orbital can be empty. It can hold 1 electron or 2 electrons, but it cannot hold any more than 2. 2 is the maximum number of electrons that each orbital can have. So let's think about this. If I look at this, the D sublevel, we said, okay, if I have a D sublevel, my L number is 2. So that means my M numbers can be -2, -1, 0, +1, and +2. I have 1, 2, 3, 4, 5 orbitals. And if each orbital can hold 2 electrons, right? 5 orbitals times 2 electrons per orbital, that gives me 10 electrons that I can hold in my D block. Now, I want to show you something really quickly on the periodic table. Okay, we're going to look at the orbitals and we're going to look at this. So I want you to start drawing with me. We're going to highlight some stuff here. Now, the first thing I want you to do is we are going to draw helium right here. Helium is going to stay right there, okay? We're going to pretend that it's not here. It's right here. Okay, so when we draw this on the periodic table, this right here, that is our S block. So those electrons going in there are S electrons. They are the spherical shaped electrons. Okay. Next thing we're going to draw, I'm going to change the color here. We're going to draw the next block over here. And I'm hoping that you can see that we have essentially a square here to the bottom of the periodic table. Okay, that right there, this is the P block. So the electrons right there are P electrons. Those are the ones that are in the figure 8 or the hourglass shape orbitals. Okay. Let's draw right here. Let's change this color again. This block here in the middle, this is our D block. So the electrons going in there are the electrons that are the cloverleaf shape orbitals. Okay, so this is the D block. The other thing I want you to remember is the D block is 1 period behind. So this is all n minus 1. Okay, and then our last block that we're going to look at, and I need to get another color here. Come on. Is it going to let me scroll down? There we go. Oh, and it didn't change the color. Okay. This right here is my F block. So these are where the really fancy jack-shaped electron orbitals are. And these are 2 periods behind. So this is n minus 2. So remember, the lanthanoids go right here and the actinoids go right here. Okay? So here we go. Let's look at the S block really quick. So if I look at the S block, if I have an s orbital, that means L is equal to 0. That means my m sub L is also equal to 0. That means I can only fit in 2 electrons, right? So guess what? We have 1, 2. That whole block is only 2 electrons wide. That's all we can fit. If I have a p orbital, that means L is equal to 1. That means my m sub L, or my m numbers, can be -1, 0, and +1. So I have 3 orbitals. 3 times 2 gives me 6. Let's count across. 1, 2, 3, 4, 5, 6. Okay, 6 electrons to fill up the p orbital. Okay, let's look at our d block. D block, that means L is equal to 2. That means my m sub L is -2, -1, 0, +1, and +2. So I have 1, 2, 3, 4, 5 orbitals, which allows me to fill in 10 electrons. You guys good with that? So let's count across the P block, or the D block. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons. So you're starting to see that the periodic table is actually designed to show us quantum mechanics. The periodic table is indeed a map of quantum mechanics here. And our last example here, if we have an F orbital, that means our L number is 3. That means our M sub L number can be -3, negative L, all the way up to positive L. Right? So that gives us 1, 2, 3, 4, 5, 6, 7 orbitals. And we can put 2 electrons in each orbital. So 7 times 2 will give me 14 electrons. How wide do you think the F block is? Let's count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Well, the lanthanum goes right here. So it's really 14 because lanthanum actually goes right there. So yeah, the F block is 14 wide. So quantum mechanics is the periodic table. Okay, so let's go back to our last quantum number here. Our last quantum number is the spin that the electron has. Mathematically, S, and sometimes it is sometimes called M sub S as well. S only has 2 values because I can only have 2 electrons in that orbital. I can either have what we call a plus spin, or +1/2, or a negative spin, or a -1/2. Okay, that is used to tell me which electron in that orbital of the 2 I'm talking about. Okay, so sometimes for just shorthand, we will put an up arrow for an upspin electron, and we will put a down arrow for a downspin electron. And notice we don't put a whole arrowhead on this like that. No, we only do a half an arrowhead. So we kind of have this shorthand where we have kind of an upspin and a downspin. And that tells us which electron we have here. Okay. Now the spin number was not introduced by Schrodinger. Schrodinger did the first 3 quantum numbers. This last quantum number was introduced by Wolfgang Pauli, okay, Austrian. He introduced that fourth quantum number of spin. And the Pauli exclusion principle basically states that no two electrons can be in the same place at the same time, meaning that every single electron within an atom is going to have a unique set of quantum numbers. So no two electrons can be in the same place at the same time. So in other words, no two electrons in the same atom will have identical quantum numbers. So each electron, in other words, has a unique set of quantum numbers. Okay? So every electron has its own unique set of quantum numbers. All right? When we get into this tomorrow, or not tomorrow, but the next time, we're going to start talking about placing these electrons using the quantum number in the hotel analogy. Now, the hotel analogy is something that I really, really like. It's done by Henry Eyring, who, for those of you who know Henry B. Eyring, who is a prominent figure here in Salt Lake City, Henry Eyring was his dad. Now, Henry Eyring studied chemistry under Einstein at Princeton. And Henry Eyring was brought here to the University of Utah to actually start their graduate studies. And before that, the University of Utah really only gave out bachelor's degrees. And Henry Eyring was one of the champions of the University of Utah in bringing advanced degrees in advanced science to the University of Utah. Now, little rival here, the chemistry building on the University of Utah's campus is named the Henry Eyring Building. Whereas at BYU's campus, the Henry Eyring Building is actually the physics building. So both campuses have Henry Eyring buildings. I've spent many, many hours in both of those buildings. I know both of those buildings like the back of my hand. So, and we will talk about this analogy tomorrow. All right. We'll see you later. Have a good day. Bye.